Example 5 from Notes 4.1, Days 1 and 2. Here we're going to be looking at characteristics of rational functions. We're going to look at a few examples and then define those characteristics. And much of the discussion about rational functions focuses on their graphical behavior near x values that are excluded from the domain. These values are going to be where we have vertical asymptotes and holes. And the other thing that's important is the end behavior. And that's what happens to y as the graph goes far to the right, x goes to positive infinity, or x goes to negative infinity. And we describe this end behavior as horizontal and slant asymptotes. That's what we're going to be studying. So let's go ahead, let's jump right in and look at a couple rational functions and their characteristics. So the first graph, number 5a, we're first going to look at the x-intercepts. So x-intercepts, we know, are points where the graph crosses the x-axis. On this graph, that x-intercept is right here. That point is negative 3, 0. And I really insist that you write these as ordered pairs to distinguish them from vertical asymptotes. The y-intercept, that's the point where the graph crosses the y-axis. If it does, and indeed we have one y-intercept here, that's at the point 0, negative 3. Horizontal asymptote is a horizontal line that the graph approaches but doesn't touch as x goes to positive or negative infinity. In this case, it's this line right here, which has the equation, and I want you to write these as equations, y equals 1. And a vertical asymptote is a line that the graph shoots up to positive or a negative infinity. It's at values that are excluded from the domain. The asymptotes, by the way, are normally denoted with dashed lines. I'm just highlighting it here. We have a vertical asymptote at x equals 1. Graph B, x-intercept, once again, points where the graph crosses the x-axis. In this graph, we have none, so we do not always have an x-intercept. Y-intercept, that would be a point where the graph crosses the y-axis. For this graph, it's not right and an exact value, so we'll estimate it. It's this point right here. I would say that's about 0, negative 1.4 approximately. Horizontally asymptote, we're looking for horizontal lines that the graph approaches but doesn't touch as x goes to positive or negative infinity. This has a horizontal asymptote at y equals 0. And vertical asymptotes, those are lines at the graph where the graph shoots to positive or negative infinity, values that are excluded from the domain. We have one here at x equals negative 2. Write that down here. And the second vertical asymptote is this line right here, which is at x equals positive 3. So we can actually have an infinite number of vertical asymptotes in our graph. Graph letter C. Let's look for x-intercepts, where the graph crosses the x-axis. Here I see 2 points, and they look like they are at plus or minus 3, 0. Y-intercept for this graph is right down here, and that happens to be at 0, negative 9. Horizontal asymptote, horizontal line that the graph approaches but doesn't touch as x goes to positive or negative infinity. That looks like it's at y, it's this line up here. I would say that's y equals 1/2. Vertical asymptote, this graph does not have any vertical asymptote. So rational functions do not always need to have vertical asymptotes. Let's go down, look at the last 2 examples. So example D, once again, we're going to get all those same characteristics and define them. So I'm going to look for x-intercepts. This graph has just one x-intercept. It's a point 0, 0. And the y-intercept, if we've got an x-intercept at 0, 0, the y-intercept is also at 0, 0. Remember, we can only have one y-intercept, otherwise it wouldn't be a function. Horizontal asymptote for this graph is going to be at, it's right here, it's going to be y equals 0. And vertical asymptotes, we actually have two on this graph. We've got a vertical asymptote at, looks like x equals -1 and x equals +1. So -1 and x equals +1. But I have a question. I guess it's rhetorical because you're not here. Notice that the graph is actually crossing the horizontal asymptote, right? That's happening right here. We're crossing the horizontal asymptote. And the reason that that's okay is because horizontal asymptotes describe end behavior. That's what happens to the y values as x goes to positive or negative infinity. So it's okay to cross it somewhere in the middle, just not at the ends. So you can cross a horizontal asymptote. Okay, that's okay. But we can cross a horizontal asymptote, in the middle, I'll say. So just not near the ends. Okay, but we can never cross a vertical asymptote, okay, because those values are excluded from the domain. Cannot cross a vertical asymptote. And that's going to be important as we continue analyzing and graphing rational functions. Let's take a look at the last graph here. X-intercepts, we have two. Once again, note the scale here. There are 2 units per line. So our x-intercepts are at -2, 0, and -9, 0. Y-intercept, this graph does not have any y-intercepts because we actually have our vertical asymptote is at x equals 0. So no y-intercept. Horizontal asymptote, we're looking for a line that the graph approaches at the ends as x goes to positive or negative infinity, and we're looking for a horizontal line. So in this case, there's none, but if I look at the graph, it seems like it's approaching an oblique line as x goes to positive or negative infinity, and when that happens, we have a different type of end behavior, and that is called a slant asymptote.